For part 2, we're going to talk about inferential statistics, focusing in particular on means and proportions. So before we do that, we need to consider this model of a distribution. This model is called the normal distribution model. It's a probability distribution, so the area under this curve equals 1. It's a model, it's an abstraction. The idea behind this model, it models a distribution of a numerical variable. It's centered on mu, right, and has a standard deviation of sigma, and accordingly the variance is sigma squared. Right? By convention, when we talk about these models, we use Greek letters. They do not have to refer to population parameters. They often do, but not always. In general, we use Greek letters when we talk about models to emphasize that this isn't a data set. This is a model for a set of processes for some aspect of the social world around us. The notation we use is we say x is distributed. That's what that tilde means, that little squiggly line. We say x is distributed normally, centered on mu, with the variance of sigma squared. Right? The spread is given by that value of sigma. Notice the property of the normal distribution model. It's symmetric. Right? It looks the same both above and below mu. The most likely value is mu. That's where the top of the hump, that's where the top of the mound is located. And you can see values really far away from mu, either very high above mu or very low below mu. They're just very unlikely to occur. Right? That's because the height of this model, it tells us how likely values are to occur. It's a probability distribution. Right? Values close to mu are more likely to occur. Values in the tails are much less likely to occur. We can also generalize this normal distribution model by thinking about a standard, or what's called a unit normal distribution model. This is the normal distribution model, but it's expressed in terms of z-scores. That means that we say that the distribution is centered on 0, and the standard deviation of the distribution is 1, or equivalently, the variance of the distribution is 1. So the standard normal distribution has the same shape as the normal distribution, but what's nice about it is it's standardized so that the mean is always 0, and we can talk about deviations, standard deviations above and below the mean. From this, we can talk about something called the normal coverage rule. Okay, we can express this in terms of the normal distribution model. We can also express this in terms of the standard normal distribution model. In both instances, the idea is the same. Right? Because this is a probability distribution, right? Assuming that some set of data follows this distribution, we can make conclusions. We can say that we'd expect 68% of values drawn from this distribution to lie within one standard deviation of the mean. We'd expect 95% of the values drawn from this distribution to lie within 2 standard deviations of the mean, roughly. And we'd expect over 99% of randomly drawn values from this distribution to lie within 3 standard deviations of the mean. To put it another way, most observations lie within plus or minus 3 standard deviations of the mean. Right? So this is the normal coverage rule, because what's useful about this is that all we need to know is about the shape of the distribution and 2 values, the center, the mean, and the spread, and we can make a characterization and help us interpret the distribution and how likely certain values are to occur. Now, related to this, using the standard normal distribution model and using the concept of z-scores, we can start thinking about finding probabilities from z-scores. So a z-score is just a standardized score. It's a linear transformation of some variable. Well, let's think about how we might find probabilities and percentiles and work with z-scores. Suppose Anne earned a score of 1800 on her SAT. So an SAT is a standardized test in the United States. And she had a z-score of 1 based on this exam score. Suppose Dave also took the SAT test, but we don't know his score. So they both took this same standardized test, but we know the z-score of Anne, and we know her raw score, but we don't know Dave's score. Well, suppose we knew that in the population, the average SAT score is 1500, and that the standard deviation is 300. Then we might say, what is the probability that Dave scored equal to or lower than Anne? Just treating Dave as a random person from the population. Right? How likely is it that Dave scored equal to or lower than Anne? Well, we might say, what is the probability of obtaining a z-score less than or equal to Anne's z-score? This is assuming that the distribution of SAT scores is approximately normal. Well, we can find out Dave's probability of having a z-score equal to or lower than Anne, or equivalently an exam score equal to or lower than Anne's, by using statistical software and using what we've learned about the standard normal distribution and z-scores. Now we can use statistical software, we can also use what are called normal probability tables. For this course we will focus more on statistical software as we've done so, and in the exams we won't ask you to work with normal probability tables, but we will go over it because it is an important concept. Finding probabilities with statistical software, well, you can visualize the distribution here. You can see Anne's z-score, and you can see that we've chunked the distribution in terms of getting a z-score less than or equal to Anne's, and getting a z-score greater than Anne's. And you can see the probability of obtaining a z-score less than or equal to Anne's is about 0.841. It's very likely to obtain a z-score lower than Anne's if we treat Dave as a random selection from the population, given what we know about the shape of the distribution of the population, which is more or less normal, and given what we know about the center and spread of the distribution. To put it another way, it's very unlikely, relatively unlikely, that Dave scored higher than Anne. It's possible, but the probability is 0.159 roughly. We could also find these probabilities with a table. The tables were more popular before we had computer software, so it's useful to go over again. You might still encounter it. The idea behind a table is that rather than using statistical software, rather than visualizing the normal distribution, we can use a table, and we can use z-scores and work with that. So the first decimal place is typically in the rows, and the second decimal place is usually listed in the columns. Each cell of this normal probability table will give the probability below a certain z-score. So for example, for z equals 1, we find that the probability of z-score less than 1 is about 0.841. Right? We can also use the complement rule because the area under that probability distribution, under the normal probability distribution equals 1. So the probability of obtaining a z-score greater than or equal to 1 is roughly 0.159. So we can compare these two approaches. We can use a table or we can use statistical software. In both cases, we get the same result, more or less, of 0.841. Now, there is an important note on output. Normal probability tables and statistical software, there may be a slight variation in the probabilities that they give out. So in this previous example, the normal probability table gives the probability of having a z-score less than Anne's z-score, or any particular z-score, while the statistical software gives the probability of z less than or equal to any given z-score. These differences are really quite minor and tend not to have much practical sense or import. So we will treat these as roughly equivalent. Right? They're very closely, approximately equal. Just be careful to keep in mind that there are differences in how people set up finding probabilities using statistical software and finding probabilities using normal probability tables. That's why we'll use the squiggly equal sign. That says that these are very close approximate probabilities. So in this case, we can say roughly the probability of having a z-score less than Anne's is 0.841. The probability of having a z-score less than Anne's, according to the statistical software, is also roughly 0.841. Right? Just a different way of looking at the probabilities. And of course, we can also compare the two approaches in terms of finding a probability greater than Anne's z-score. What I like about the statistical software is you can see that it is just a distribution. It is a normal probability distribution model in which the area under the curve is a probability. Right? The total area under the normal distribution curve, standard normal or just the normal distribution model, the total area under the curve is 1. Right? The probability of having a value under that curve is 1. But under certain ranges, intervals of that curve, some probabilities, some z-scores are more likely than others. Okay? Some z-scores within certain ranges have higher probabilities. And that's where the normal coverage rule comes from. The normal coverage rule just says we expect most of those z-scores to lie within that middle part of that normal distribution model.